Hello, my name is Seidel. I work for the Institute of Building Construction at the TU Dresden as a research associate. Today, I'm going to present you the main points and the main results of the plusROOF research project, which was done by my former colleague. Glass skylights are popular in new and existing buildings. They provide natural lighting and improve the look of interiors. The structure itself can become a design highlight, especially with large spans. In order to realize such, steel substructures are generally used. However, steel and glass elements are usually complex and expensive to build. This contradicts the goal of establishing industrial manufacturing processes to the construction industry. In addition, the current construction method severely restricts the scope for design. One possible solution is to bond the glazing directly to the steel substructure. Only a few minor work steps are required before bonding, which considerably reduces the production effort. In addition, the design scope is extended and the substructure remains undamaged as there is no need for welding work. The structural bonding of glass is regulated by standards, but only on selected surfaces. This does generally not include corrosion protection coatings. However, as these are elementary for the intended construction, further investigations must be carried out. This brings us to the main points of the plusROOF research project. First, we investigated whether the adhesive bonds well to common anti-corrosion coatings. To do this, we tested various coatings and application methods in small part tests. Material aging was also an important point, as can be seen here in an outdoor weathering stand. We used the results from the small part tests to produce steel glass roof elements component size to test their practical feasibility. The first sample, measuring 300 times 400 millimeters, had two rectangular insulating glazings. These glazings were not inclined. If you compare the test specimen with the roofs from the beginning, some differences become apparent. Among other things, the skylights are to be double curved, which changes the inclination of the glazings. Furthermore, triangular glazing are to be used instead of rectangular glazing as seen in the hand samples. In order to adapt the component test to the desired circumstances, we have developed a second demonstrator, as can be seen here in the picture. This one reproduces the skylights even better. The dimensions of the individual elements were also adapted more close to the real application. A planning tool, also developed in the research project, was used for this demonstrator. It can be used to create double curved skylights under parameter control. It not only provides visualizations, but also construction details of the glazing and the substructure. For the choice of the best coating, adhesion tests on H-shaped test specimens were decisive. The ETEC 002 Part 1, a guideline for bonded glass constructions, regulates such tests. The best results were achieved by the polyurethane coating that met all the requirements of the ETEC. The steel profiles of the hand samples were therefore also provided with a polyurethane coating. When producing the adhesive joints, explicit attention was paid by replicating the real installation situation. This required the adhesive to be applied underneath the roof. The reproducibility was ensured by these hand samples. All the results ended in the already seen 5.5 meters times 3.1 meters demonstrator. This replicates the double-curved skylight roofs on small scale. Further component tests could be carried out with this demonstrator. The test program included tests for air permeability, driving rain tightness, and resistance to wind load of the system. The test program was based on the product standard for curtain walls. At the time, there was no such normative regulations for glass skylights. We were able to use our 6-meter tall and 3.6 meter wide facade test wall in our laboratory for the component tests. The test for air permeability, positive and negative pressures were applied on the roof. The air permeability through the system was measured continuously. After that, we installed nozzles on the test wall to test the driving brake tightness. They sprayed the roof with water while simultaneously creating an overpressure in the facade wall. This allowed us to test the system for any leaks. The last part of the test examines the deformations of the system. The design wind loads were applied on the roof, and the deformation of the substructure and the glazing were measured continuously. In some cases, even with excessive pressures of about 200 to 300% of the design wind load. The roof delivered excellent results. It achieved an exceptional air permeability and driving brake tightness class. Even at 150% of the design wind load, no damages occurred, and the deformations remained below the permissible values. Let us come to a small conclusion. A suitable coating for the structural bonding of glass to steel was found and proven in small part tests. In order to transfer these results to larger components, hand samples and a demonstrator were produced under real conditions. The load-bearing capacity and the serviceability of the system were demonstrated in the component tests. The test results lay the foundation for approvals and therefore for future projects. So the only question that remains is when we will discover such a roof above our own heads. Thank you for your attention.